area. All right, so, yeah, math, chemistry, how can it be the same thing? Well, there's lots of things that overlap. Half-life is one of them. So explain, you said you talked about it math, do you remember?
No.
Oh, okay. Well, what's the word half mean?
Half. 0.5, 1 over 2.
Very good. 0.5, 1 over 2. All right, good. And the word life means, well, it's a little bit heavy there. But basically what this means is as soon as an element is created, whether it's in a lab or in nature, whatever reactions create elements. Okay, and some of these, like uranium, was created when the Earth was created. Okay, uranium was created when the Earth was starting to form, and that's called accretion. When things are spinning in space and they start to get hot, and then they start to get bigger, and when they get bigger, they start to have gravitational pull, and they start pulling in things that are around them, like asteroids, chunks of rock, stuff like that. So when the Earth was formed, uranium was formed at that point. And ever since then, uranium has been slowly decaying. The reason I use uranium, go to table N, look at the bottom. How many isotopes of uranium are on there? 3? All right, we'll just pick one. So let's pick the bottom, very bottom, U-238. Its half-life is 4.5 billion years. 4.5 times 10 to the 9th is 4.5 billion years. So since the Earth has been created, uranium has been on the Earth, or in the Earth, however you want to look at it, and it's been decaying. It's been releasing alpha particles that whole time. Okay. Other elements have a much shorter half-life, and they weren't necessarily created billions of years ago. But whenever they were created, they start to decay immediately, and their half-life is much shorter than uranium. So for example, look at francium-220. It's up near the top-ish. Fr-220, what's the half-life? Somebody read it, please.
27 seconds.
Thank you. 27.4 seconds. So francium-220 has a half-life, it's in the seconds. Uranium's in the billions of years. Well, guess what? The definition applies to both of them. It's just francium's is much shorter than uranium. So what is half-life? It's the time it takes, I want you to write this down. I will write it, but the time it takes for half of the particles, now I could go a couple different ways with this. I kind of give different definitions every year depending on how I feel. So I think I'll go with the stable route. The time it takes for half the particles to become stable. Half of the particles will become stable. You've already learned what that means. So if we use table N as an example, all right? So again, the definition, I decided I'm not going to write it. That's the time it takes for half of the particles to become stable. Let's use carbon-14 as an example. So carbon-14, write this down please, decays into what? What particle does it emit from its nucleus? Beta. So 0, -1e, it turns into nitrogen 14. Okay. So this is called a decay equation. Natural radioactivity, natural transmutation. I'm trying to go very slow and kind of play off of what we know to apply to something new today. So we know how to do this. We understand how to look this up, what that means, right? It's radiation coming out of the nucleus. This is unstable. It's radioactive. This is stable. Let's write that. Unstable. This is stable. And remember, that's because of the neutron to proton ratio. All these things we've already learned. Just reviewing. So, it's unstable, so it emits radiation to try and become stable, right? It sneezes, it turns into something new. This is the exact one they used in that video. Okay. Well, what's the half-life of carbon-14? It's 5,715 years. So, what does that mean? Now you gotta go to the chips here. So you should have 16 chips. So pick one color, or you should have 32. 16 of each color. Put 4 rows of 4 of one color on your desk. 4 rows of 4 of one color. I'm gonna use red and yellow. So I'm gonna do mine up here. You have yours at your desk. I need more red. Alright, so there's my 4 rows of 4. Alright, we're going to be doing like 3 things at once here. That's why it looked confusing when you walked in, Liz. It's not, because we're going to go slow. But alright, so once you have your 4 rows of 4,
That's 3.
4 rows of 4. Then what you're going to do, somewhere in your notes near this, please, I'm going to show you how we set these problems up so we can answer Regents questions. So we can talk about it, you can understand it, and that's great. But can you answer questions on Regents? That's obviously really important. So I use this chart technique to kind of teach half-life and show you how to answer problems. So we'll go through this example using our bingo chips and the magnets here. I'll apply it to a chart, which you don't know anything about yet, but then we'll take what we learned here and then we'll do a practice problem. Hopefully we have time for that. Okay. If not the end of the world. We'll pick up with this tomorrow. Okay. This chart will save your life on half-life problems. Mass, time, half-life. It's imperative you remember the top of the chart. Mass, time, half-life. Okay. When I showed you the radioactive discs the other day and with the beeping, the Geiger counter, those are going through half-lives constantly. Some are longer than others. But that beeping will eventually go away. They'll stop giving radiation off when they go through multiple half-lives. And I'm trying to use this to teach that. So let's say a sample of carbon-14, all right, this is natural. Let's say somewhere out there in the world, this is created. All right, so carbon-14 is created, and you have 16 grams of it. Let's say each magnet here or chip is 1 gram. So we have 16 grams of carbon-14 up here and on the desk. Well, in our chart, we're going to write 16 grams right here. So 16 grams is what we are starting with. That's the initial mass, the original mass of carbon-14. Again, this could be created in the lab, it could be created outside in nature, but when this isotope is initially created, however it is created, it immediately starts to decay. What is it doing? It's emitting beta and forming nitrogen because it doesn't want to be carbon-14. It's unstable. It wants to have a stable nucleus, so this happens immediately, and it progresses for 5,715 years. So, in a chart, we write this as our original mass, so again, 16 grams. We write this for the time. Why? Because we act as if time has not started yet. As soon as this is created, we're assuming time, the clock has not started to run. So the original mass, when no time has passed, is 16 grams. So nothing has happened to this yet. It hasn't started to decay yet. It has not gone through a half-life yet. If you're confused, don't worry. When we get through the end of this example, it should all click. Okay, so now, you got carbon-14, you got your 16 grams. Okay, hit your stopwatch. Now time starts to go. Well, what happens is, slowly, over this much time, slowly, so from time 0 all the way up to 5,715 years, individual particles will start to transmutate. So slowly, so let's say 100 or 500 years go by. Well, this particle will decay. What does that mean? It turns into nitrogen. Well, then another few hundred years pass, and these two particles decay, and they turn into nitrogen. And this keeps happening for 5,715 years. Once this time is reached, who's following me? How many red, how many yellow should we have? Right, equal amount. Because what happens is this number tells me the half-life, which means half of these particles have turned into nitrogen. So if I started with 16, after one half-life, 5,715 years have passed, and we should have 8 of these particles that are not red anymore, but they're yellow. So 1, 2, 3, 4, 5, 6. I want you to do the exact same thing here. 7, 8. So go ahead. Even if you were like, I get it, do it. I want you to see it with the chips. Okay? So one particle at a time, over time, so over those 5,715 years, they will start to decay. Do not do chunks of particles. Do it like I did it.
Wait, is it just in like random order?
Yes, it's random. It actually is a big mystery to the scientific world. No one knows why certain particles decay versus others. But they do know half of them will decay in a certain amount of time. So I used to teach this incorrectly not too long ago. I used to just get rid of half of the particles on the bottom. I used to do the same thing, but I would get rid of the red on the bottom and fill them all with yellow, so it was like even chunks of red and yellow. That's not how it works. I learned more myself and realized that's I'm teaching it wrong. It's random. The particles are random. Okay? So this is exactly how half-life works. So if you could zoom in on those chips that I had in the back that were giving off radiation, this is what they're doing. They're doing this over time, depending on how long that time is. Some do this very quickly. Francium does this in 27 seconds. But carbon takes 5,715 years to do it. Okay? So this is the gist of it. We're not done, but this is kind of the most important part, is understanding what happens during this time. This is what happens. Particles literally turn into new particles, transmutate, giving off radiation, and now these yellow ones, or whatever your color is, are more stable. Now let's back to the chart. So after one half-life, this much time has passed. Well, how much of the carbon do I have left? Count. How many? 8. Remember, each one's a gram. So we have 8 grams. That's why it's called half-life. If you start with 16, and after one half-life you have 8 grams, that's half of what you started with. 1 over 2, 0.5. Right, Skylar? Right. So that's how we do half-life. We first need to know, okay, what do we start with? Then we need to know how much time passes, and then we just do the math or we figure it out using diagrams like this. Okay, but we're not done. Let's say another 5,715 years pass. So we go through 2 half-lives. How much total time, remember we hit that stopwatch. Once that watch is going, it's going and going and going. We can't stop it. So how much time has passed now? We started at 0. We went to 5,715 years. Now we have, what would that be?
Another 5,000.
Another one of those, which is 11,430 years. And what do we do here? How many would we take away? How many red am I taking away?
4.
Half of them.
4.
It's a half-life. I have 1, 2, 3, 4, 5, 6, 7, 8, so I'm taking half of them away. Every time you take half. That's why it's called half-life. So go ahead, humor me. Do it with your chips, please. All right, last thing before the bell rings. No homework. Definitely no homework.
Dude, can I also show you that? Like later.
What do we put here? How much is remaining? How much of the carbon do we have left? 4, because that's half of 8. Is it starting to make a little sense?